Yeah, hello everybody to our first webinar in 2021. I would like to welcome you. My name is Rainer Schramm. I'm the General Manager of FLUXANA, and I would like to present you today our newest development, the VITRIOX 4+, a new fusion system we have recently developed. But before I start with explaining you the machine, I would like to come back to the basics of fusion. So why are we doing fusion? So the first thing is that we would like to dissolve a sample into a glass to get a homogeneous sample we can then analyze by X-ray fluorescence. So normally you use a kind of a dilution of 1:8 or 1:10 between your sample and your lithium borate, your glass former. Then you homogenize the whole thing. You make a homogeneous liquid by heating it up. Then you pour it into a mold so that in the end you get an ideal sample, a fuse speed. That means your original sample material is dissolved into a glass. Like you can compare it with dissolving a sample into a liquid. So this is the first picture image of our new fusion system. It is wide about a classical 6-position fusion machine like you know it. The deepness is like a laboratory bench, but we put it on the floor so that we have some space to store samples, so that we can manage to fuse up to 16 samples in one run. Yeah, so the idea is here to have a machine with a high throughput, fully automatic, so that you can use it for all kind of different applications. And this gives you then some flexibility, more flexibility than just a benchtop fusion machine like you have it today. Let us have a deeper look into the housing. So for example, here you see the sample magazine where we have sample holders. Each sample holder holds 4 samples. You can store 4 holders so that in total we have 16 samples in our storage. The upper station has a special function. It is the cooling station in the same time than the storage. And you see here how the crucibles are placed in the holder. So they are looking side by side. And underneath the crucibles sits the mold, so that you have 4 molds and 4 crucibles sitting in one holder. And here on that cooling station, you can see that the cooling is done by compressed air, which is the best way we use to cool down beads, like we do it on all our other fusion systems. Cooling down by air has the big advantage against the ventilation cooling, that you have less breakage of beads. You don't need so much non-wetting agents, and the bead is releasing generally much easier than if you use just the ventilation. Yeah, so this is why we kept our good way to cool down the beads by pressed air. On the top here we have the furnace, and the muffle furnace is a round furnace like we have it on our other VITRIOX fusion machine. The round furnace allows us to place the heating around, so this makes a uniform heating to make sure that every sample gets the same heat. And we have our lift bottom furnace. That means that the door is the bottom, so we open to the downside, and in this way we lose much less heat when we open the furnace than you know it from a classical muffle furnace principle. So this all leads to a higher precision and higher accuracy in making fuse speed and X-ray fluorescence analysis, and this is the design you need to do that. On the top of the furnace we have the possibility to open it. That means if you do, for example, oxidation reactions inside for ferroalloys, then all the volatile parts can escape here through the chimney. And If it's closed, we have a quartz glass on top, a window, so that you can watch your reaction inside. For the 4 samples, there's an intelligent placement. That means you can always watch one sample and then it just moves to the next, so that you have all 4 samples under control. But what is the motivation for fusion? Of course, it is the high precision and accuracy of this sample preparation. To get this, we have to look a little bit on our samples, and let us assume this is a bead and we want to analyze silica. Then we only have a certain penetration depth into that sample. So that means if we want to see a high precision finally, we need that this silicon is really distributed homogeneously in the whole sample, so that this small layer which is analyzed is representative to the whole sample. If we look for iron, then of course the penetration depth is much deeper, but again, it must be distributed homogeneously. But it's not only in the deepness of the sample, it's also in the surface where we need a homogeneous distribution. Then only then we will get the high precision. The other big motivation is the easiness of calibration in fusion. That means that we can either use certified reference material, we dissolve it into glass, and because of the dilution, most calibrations are not so curved, and we know it from press palettes. So we don't need to do so much matrix correction than in press pellets. So this is one advantage. The other advantage is that we can use pure chemicals to design our calibration beads, and in this way we can fill gaps we wouldn't be able to fill in a press palette. So both are the easiness of calibration and the high precision, because it's a very homogeneous sample. This gives us the motivation to do fusion. Of course, additionally, automation is an argument, and like we do it in the FLUXANA fusion machines, that we calibrate each machine for temperature, then you can guarantee that in every laboratory a FLUXANA machine is giving the same beads, and then of course you can transfer calibrations just from one lab to the next. This makes the whole technology very flexible, and also this reduces development costs and time. But to get high homogeneity, we need to look on all the variables which influence our system. And a very important one is temperature. The temperature is influencing the viscosity of our melt. There's also the surface tension of the melt. There are some elements which are reducing the tension, and then you use non-wetting agents to support that it's going back, and that the melt is not sticking too much to the wall of your platinum ware. The fusion time is very important, and especially if we are looking on volatile components like sulfur or halogens, then temperature and time became very important, because they will influence how volatile is your components and how much you lose during the fusion. And only if both you can keep very constant, then it's no problem, for example, to analyze chlorine in fusion. Another very important point is the temperature distribution, so that every crucible sees the same temperature, so that you don't have different results depending on where your sample have been during the fusion. Homogenization, so how is it mixed inside? The ratio sample to flux, of course, influences the viscosity together with the temperature. And the condition of the platinum ware also is important. So how rough is the surface? How sticky is your melt to the surface? Are there scratches in the mold? So also these are important points which will lead to a successful fusion or not. Last but not least, there could be some contamination, either from the platinum ware or, of course, from the furnace system. That means things are falling down from the ceiling, or you have cross-contamination from one sample to the next. or any kind of dirt which was collected in the furnace. Yeah, so these are all the parameters which will influence our system, and only if we have it under control we can get a high precision, high accurate X-ray fluorescence analysis. But let's have a deeper look into our temperature, because that is, in my opinion, one of the most important parameters. And I would like to give you an example. Cement, perhaps 1 to 10, 1 to 8 diluted. You can fuse this, for example, at 1075 degrees. The moment the autosampler introduces a sample, the temperature will drop because you open the furnace. You introduce your sample, you close your furnace, and then, of course, the temperature is going up again. It's stabilized. Then for pouring, you have to open it again, same situation. So the heating, of course, the heating will make sure that your furnace is stable on the same temperature, and in the moment you destabilize it, the heating must come back to the same temperature than before. Again, stability in temperature, same thing again, and from here, when it's stable again, you can make your next fusion. Yeah, so this is the general procedure here. If we look on the agitation, then there we have introduced something new. Because we have a round furnace, we rotate our samples all the time. That means after introducing them into the furnace, we rotate the bottom like you know it from the microwave. And in this way, we homogenize the temperature distribution in the furnace, so that like your food in the microwave, also the samples here every sample sees the same heat. So this guarantees an extremely high precision. And then once it's liquid, we do a fast agitation, really to homogenize it inside the crucibles. If we look on the samples, then of course they are solid in the beginning. During the heating up, they get liquid. And then step by step, during the agitation, it gets more and more homogeneous. And when it's really homogeneous, we pour it into our mold and then cool it outside in our cooling station. Of course, when you have such a furnace, the important point is also how long time does it need to heat up. So when you come in the morning, how long you need, and in this case, our furnace needs about an hour. And we have integrated an time-based heating. That means you can program energy saving times. That means overnight you can switch it off, and when you come in the morning, it's already on temperature. So when you program it that it's 1 hour before you start work, it will be heated up. You can switch it off over the weekend. So in this way, it's like green energy. So we save energy by this management. In a routine fusion process now, and I come back to my cement example, we would then start with introducing 4 crucibles at once in the furnace. We would fuse about 12 minutes. We will pour our 4 samples, and then, important, there comes a stabilization time. That means how long does the furnace need to come to the same conditions than before the first fusion? So that means when we repeat our fusion for 4 samples, that we get exactly the same beats afterwards than in the first run. And this stabilization time you can program. It will be for routine 1 minute. And let me say, if you do chlorine or fluorine fusions, then probably it should be something around 3 minutes to give a little bit more time to have exactly the same temperature conditions than before. So then you do your second fusion here. That means we have a time advantage here. Once we fuse 4 samples and then take it out for cooling, while it's cooling, we can introduce already the next 4 samples, so that the throughput of this 4-position fusion machine is higher than on a classical 6-position fusion machine, because there you need to wait until the 6 samples are cooled down. The user has exchanged the 6 samples, and in this time already the second run, the 8 samples are finished. Yeah? So this is how we could improve our throughput in the fusion. But how does it behave now in different applications? Yeah? So let us assume again our cement example. So we fuse 12 minutes, 4 samples for cement. Then you say, now I want to do sand. And this means we need a higher temperature. So automatically the furnace heats up to get the conditions for sand. Then the samples are introduced. If it's pure quartz, you would probably need a fusion program of 20 minutes. And after that, if you do a limestone, you cool it down again, and you will continue with the next fusion. Yeah. So you see the system is able, fully automatic, to handle different applications, different timings, different temperatures, and this up to 4 different applications. Another special application would be something like ferroalloys or slags, where you need an oxidation step before. So let us assume we will do something like ferrochromium. Then we would mix our ferrochromium with, for example, strontium nitrate. We make an oxidation mixture. We put it in a kind of a dumped flux bath, and then at a temperature of 1025 degrees, for example, we will make an oxidation for 8 minutes. Over the furnace window, you can observe this so you know when this is finished for your application development. And after this is done, there will be already a melt where all the ferrochromium is now oxidic, iron oxide, chromium oxide. The flux is still solid. After that, you increase the temperature and the real fusion is done until the whole mixture is liquid. And then you do the homogenization to make a homogeneous melt. You pour it, and so it means in 25 minutes you have done 4 ferrochrome fusions. If you want to repeat the same thing, of course, you have to cool down and then to restart the whole thing. Yeah? This is an example how you can use the management of the system to do even different steps in one fusion, one application program. But important is how this furnace is constructed. So we have our heating elements which are sitting around the furnace. We have a protection tube which protects the heating elements from the samples. Very important. So this guarantees that they last much longer than if you don't have this kind of protection. And even in a maintenance, this tube could be exchanged easily so that once this is contaminated, you can also replace it from time to time to keep your furnace safe and clean. The agitation is done here with the bottom, and we have either the slow agitation or the fast one. The fast one is then accelerating this in one direction, stopping immediately, and after a few seconds in the obvious direction. And this means, if we look on these pictures, that the melt is really going up on the wall, and once it's stopping, it's falling down. And then you turn around in the other direction, and this is a really efficient way to mix. And it's only possible if you have this round furnace design, that you have this circle agitation. And we made a bachelor thesis to find out what are the optimal agitation speed for the different applications. And it was very clear that there's always a kind of a limit where underneath it would not work. And if you go over it, then you get very homogeneous melts and then also high precision beads. And so that we could save already in the system for all the different materials the agitation speed, which is optimal. But let's see now how the temperature stability is influencing our analysis. So let us assume we have 4 cements and we fuse them. And of course, when it's all true what I told you, then you will see for all 4s, for the main component calcium, a fantastic standard deviation, a very high precision. But also for the volatile element like sulfur, you will see the same. But the question we had is, what happens if, for example, you place only 1 crucible in the system and you repeat this 4 times? Yeah? So like you see here, there's not a real difference. So you even could only use 1 or 2 or 3 and whatever place you choose, because of the turnaround It's always the same conditions on every position. Yeah? So in this way, it is guaranteed that the system is as flexible as possible. The other important point was, how is the cross-contamination between the crucibles if you have different materials inside? So for example, if you have here pure iron oxide, we have here a high phosphor sample, a dolomite with high magnesium, calcium, and a slag. And if we look here on the analytical results, we can see that even the high iron is not really influencing the certified values we find in the analysis for the other materials. The same if we have high phosphorus and we have in the neighbor sample no phosphorus, we don't find phosphorus. Yeah? So it is really safe from a classical fusion point of view that we have cross-contamination. But in case you have a sample which spites sometimes, you could use lids. Yeah? So we have lids for all these crucibles, and then you close them, and then you are 100% safe that there is no cross-contamination in case your samples tend sometimes to spit around a bit. Now I have an example for a classical calibration for our raw material set, which is distributed all around the world for a lot of customers. And here I show you the calcium calibration, where calcium is presented from 0 to 100%, so an ignited limestone down to a dolomitic limestone, gypsum, slag, and so on. So we have different certified reference materials, which gives a very nice calibration curve. And we also have validation samples which then prove that the calibration is working perfectly from this kind of fusion beads. Also, I put you the volatile example, the sulfur, which is directly depending on the temperature distribution. And of course, the high values in the range of 50 to 60% are coming from gypsum, and the low values are coming from cement. And this is a high slag cement. And also here with the validation samples, we see that we can fulfill here all the needs of industry, which are common. Last but not least, here a summary for you, and you know that this will be uploaded on the YouTube channel, so you can also watch this later on in detail. And this is a comparison for different materials like cement, a rock sample, iron ore, gypsum, and sand, also fused at different temperatures, but all measured in the same calibration, and the maximum deviation we see from the certified values is here 0.4%. All the rest is in a lower range and absolutely in the range which is typical for very high precision analysis. So if I summarize now the technical details of that new machine, we have our round muffle furnace, which gives a lot of advantages concerning a homogeneous heat distribution, the agitation possibilities. We have absolutely a coal-to-coal process. That means the user is not in touch with any hot surfaces or hot samples. So even the platinumware is always come cold if it comes back. We could automate it to 16 samples. That means even if you buy it only for 4 samples, you can just later on also extend the machine to 8, 12, and 16 samples, just with a small software change and with additional holders you need. It's a modern network concept, so the user interface is Windows, what we use. So you are open to the Windows world. For example, if you would connect to LIMS or any kind of network connections you need, or whatever, barcode readers or whatever you want to connect, this is all ready for the user interface. And like I said, up to 4 applications could be used in one run. So now at the end, I want to show you the video so that you see really the machine in action, which is running now 1.5 years in our laboratory, where, you know, we have an accredited laboratory where they really use it hard. And so this is the sample storage where you see all the different racks with the platinum molds. And here you see the user interface where you have the 4 different holders, which you can load with different applications and times, so that you can just program what you want. And then here you have a drawer where you put the samples, and this is the user interface for putting the samples and taking them back. Yeah, and then the autosampler is doing the job. So the only thing you do is you introduce the samples, and that's it. The autosampler is also checking if the crucibles are there and the molds, so that there is no mold missing. Then the autosampler places it into the furnace, and yeah, fully automatic, the furnace is closed and the temperature is heated up back. This is the homogenization of the temperature. So like I said, in a microwave, it's turning all the time until it's liquid. And this is the high-speed agitation in both directions, so that you really have, that you mix it inside. And because all of our crucibles sitting on a circle, it's exactly the same stirring for every crucible. So once it's finished, the autosampler comes back, takes the rack, and pours all 4 samples at once into their molds. Yeah, and so in this way, we guarantee that every melt sees the same time, same temperature. And once it's cooled down, you just take back crucibles and molds. This is already after the cooling. That means in between it was sitting about 6 minutes in the cooling, and then you can ask the autosampler to give you back the samples. Also important is to know that you can interrupt the whole process. That means once one sample is fusing, you could unload finished samples, you could load new samples. This is already going independently, so that you can really run the machine in a continuous operation. So samples are going in, samples are going out all the time. Yeah. Or you just load it in the evening, full with 16 samples, and in the morning you have 4 different applications fused. Okay, that's it from my side. I thank you so far. And here you see also that we will continue this webinar series, so that in February is our next one. And now I will have a little look on our questions. So there are different questions here. Okay, there is a question from the audience. If you only do one sample, does this affect the balance of the fast rotation like in a centrifuge? It does not, because the crucible itself is fixed during the agitation. That means it will be held by the bottom, and so in this way this effect doesn't play a role. Then there is another question: what is the maximum temperature? We can heat it up to 1250 degrees, so that you have enough room, even if it's, let me say, quartz, or and you do this with a low dilution, or if you do phosphates, these are very high viscous melts, then you need a 1250 degrees, and this is no problem to run it there. Are there any more questions? There is, what is the material of the heating element? This is molybdenum silicide. Then there is something around the cost. Of course, the cost is depending on how many samples you have. So we have split it in a way that you have a basic model with 4 samples, and then you can just extend it to 8, 12, and 16. And of course, we will be happy to give you a quotation. Just contact us directly. So are there any more questions? Not for the moment. So then I would like to thank you, and we are 100% in time. I thank you very much for the attention, and I hope we will see again in our next webinar. And of course, if you have any more questions, you could just drop an email or give us a call. We will be happy to answer it to you. Okay, thank you very much and goodbye. Have a nice week. Stay safe and healthy.